So, Jorge, one of the things that'll be great to talk about today, we always talk about these dispersion models in terms of where methane goes when it's released. But I think a lot of people don't really know that air is or has mass, and air is a fluid, and that these different particles of air interact with one another. They have different mass, and so therefore they have different buoyancy, and they disperse differently in the atmosphere. And I guess the whole point here is, what is the impact in terms of what is going on with the release of methane and where it flows in the atmosphere?
Once methane is in the atmosphere, it's subject to everything that the atmosphere is doing. And in general, we understand the atmosphere in terms of conservation of mass, meaning that whatever happens in the atmosphere must be continuous within that atmosphere. Meaning you can't destroy masses, you can't create, weird vacuums or anything like this. So by conservation of mass, if you displace some amount of air or some amount of air that has mass, substance, because we feel it on our faces when we're riding our bikes or our motorcycles or convertibles, if you have one, because it has mass and it's somehow been displaced, typically by injecting energy into it, then another mass of air adjacent to it has to come in and take that place. And that's how wind is generated. And that's how eddies and vortices and all of these structures that we care about in terms of modeling the way the air moves are generated. And within those structures enter another gas, methane, that gets carried along within those and taken from point A to point B where we can measure it.
To know why the methane is carried from point A to point B, because we're only away from the source if you're measuring at the edge of a facility. And so we're going to have to work backwards to understand where that methane came from. And based on the wind speed, wind direction, all those ambient conditions, all those eddies, all that turbulence, understand how much would have been released at that source in order to arrive at the point where we are at the edge of the facility.
That's right. And that reconstruction, because it's a reconstruction problem, is entirely based on conservation of mass. So conservation of mass is what underlies the building of the models like the one that we have in our simulator tool. We talk about advection, diffusion. All these things are expressions of conservation of mass within a continuous fluid. And because of that, and because we know it to be true, because we're not living anywhere near a black hole or anything weird in the universe, we can do that reconstruction problem within a computer and use, the methodologies that are available in order to back out that answer, to say, hey, this is the amount of mass that had to come from this particular place in order to create this dispersed methane within this local atmosphere. And these are the motions that compose the wind in the atmosphere, and the methane will be carried within those as it's released in the atmosphere to be picked up by our sensors.
So if I'm understanding you correctly, these factors influence how the air moves. And how the air moves determines, if you release methane from a known source at a known quantity, how much methane will appear at a given place and a given time at the edge of the facility where our monitors are located. And if you don't know how those factors, those forces behave with one another, then you will misunderstand where the methane came from and in what quantity it was released, right?
That's right, because unfortunately, methane is invisible to us. Or in some sense, there are detectors that can see methane moving around in the atmosphere, but we don't have a way of seeing exactly how this is happening, right? And so we one of the things that we can do is detect in spots and then use a reconstruction, use our modeling capability, use conservation of mass, conservation of energy, and all the things that describe the local atmosphere and give us a way to reconstruct a wind field to say, okay, this is the trajectory and the path that the methane must have taken in order to get to our detector. And because we know that, or because we can make an estimate of that, then we can say, okay, then this has to be the amount of mass that was released in order to create this simulated reality.
So Jorge, and one of the times that we were talking, I said, we're using all these terms. We're using diffusivity, we're using convection, advection, all of these terms. And very quickly, folks came to me and they said, you realize that many folks have no idea what you're talking about. And as I was talking about it more and more with you here in the office, We were talking about things that people may or may not even understand, starting with like what really is air and what is mass and what is the preservation of mass and how do you think about one fluid within another fluid. And so in an effort to better understand for the wider public what's going on and things like the simulation tool and what a forward direction model is, it's probably best to go back to the beginning. And I don't know exactly where you want to start, but how should the average person out there, when they're looking at something like the simulation tool, how should they start thinking about just like what is air, what is a fluid, what is movement within air, what is the preservation of mass? And I don't know, I mean, feel free to take it in another direction if you think there's a better way to frame it up.
Air is fundamentally a mixture of gases, right? And our experience with gases and with air has everything to do with the way we feel it because we can't see it. And most gases in the atmosphere, except for maybe if you can imagine the smoke that comes out of a campfire or the stuff that comes out of the tailpipe from a diesel bus or something like this, most of the time we can't see the mixture of gases that are in air. But they have mass, they have substance. Each one of the little molecules of that air is very, very, very far apart from the other one in general, but they do interact with each other. And it's those interactions of that matter, of that substance, that then cause the flow of air. And in that flow of air, you can insert another gas. So, for instance, the light blue balloon here might represent air or a parcel of air, which is a way of thinking about air in terms of parcels or encapsulated amounts of air. And this thing has mass, right? It falls under gravity. It makes a little sound. You can feel its substance when it's in the balloon. It's very difficult to feel the substance of air when it's not encapsulated this way, but it certainly has mass and substance. Similarly, methane has its own way of expressing mass that is different from air. It's a little lighter than air usually, which is why this balloon's a little smaller. And so that's going to matter in the way that they interact with each other. But a mixture of gases in the atmosphere, one gas is almost free to live with the other gas because there's so much space in between molecules that some mass of methane can exist in air without a problem, without being interfered with. But it can be pushed around by the air. So a mass of air can push a mass of methane around and move it. And that's how we understand basic transport of a gas is air pushing onto another gas and moving it along that wind. And the wind is generated by the currents in the atmosphere that express themselves down at the surface near the places where the methane is being released. And the gas is emitted and literally being pushed around by that mass of air.
That's a good way to illustrate it. Let's go super simple. Most people hear the term mass and they're thinking about a person stepping on a scale or some sort of weight on a balance beam. Mass and air, help sync that up for folks.
It's easier to think about it in terms of water because water is a little bit more, is denser, and liquids express mass in a way that we feel it a little bit more. But it's exactly the same thing. So what happens to you when you dive into a pool? And the deeper you go, your ears begin to hurt. And your ears begin to hurt because of the pressure of the water that's above you. Air does the exact same thing. We have a certain pressure down here at the bottom of the atmosphere relative to the top of the atmosphere. And we feel that pressure, but we're accustomed to it. We've evolved to be living in that, so we don't feel it. But underwater, we immediately feel the depth of that water column. And that is literally the expression of its mass in terms of a weight because it's in a gravity field, because the earth is pulling on it and causing your ears to hurt, which is your experience of that.
And so simply being that we're a mile above sea level here in Denver, there's less air on top of us than say if we were at sea level in Florida, right?
Correct. So, and that, you heard me talk about pressure now. So now we're talking about pressure and mass. Pressure and mass are actually the exact same thing. Pressure is a useful quantity when you're talking about gases and fluids, but they're all expressions of mass. They're all different ways of relating the mass and the substance of something.
Another term that gets thrown out a lot is fluid. right? And so oftentimes when people think of fluids, they say, hey, hydraulic fluid, right? But when you're talking about it, oftentimes it's interchangeable between water, hydraulic fluid, methane. Can you express that a little bit more?
I think the easiest way to talk about that is to say not solid, right? So this desk, solid, very solid. It does not flow in any discernible way. Under some extreme conditions, it might, but as it is in our everyday experience, wood, concrete, things like this that are solid, they don't flow. They don't flow past each other. And here we are with the balloons again. So solids are usually made up in they're if you look at a microscope of a solid, they're in these fixed arrangements of the particles of them. And so the whole thing has to move together. They can only move like this, right? Whereas fluids can move relative to one another. And that's the reason they flow. That's where flow comes from. It's because the mass of, in this case, methane and air can flow relative to one another and affect each other directly, but also flow and move relative to one another, which can't happen in a solid.
So let's think of another point, right? So you said pressure is mass. The two are interchangeable. Mm-hmm. And then we're always talking about wind, right? When we're talking about the simulation tool, you can adjust the wind speed. We're talking about wind being an integral part of quantifying the emissions of these facilities. These are things that we think are obvious. And oftentimes when I'm talking to folks, especially when I'm brought in to be like a guest for an undergrad class or something like that, it gets down to really what is wind. And oftentimes I explain to folks that wind is actually a form of solar energy. And their mind is blown in many cases. And so one of the things that's actually happening that I don't think people fully understand is that what the solar receipt, the solar coming in to the Earth's atmosphere is causing is a change in pressure in the atmosphere. And these molecules, these balloons in your hand, flow from a high pressure to a low pressure area. And more or less, that's a vast oversimplification. That's what's happening with wind. And so help sync up for people what is actually happening between mass, pressure, wind, and how these things fit together in terms of a transport model, which we'll talk a little bit about as well, I'm sure, given that's foundational for a lot of the work that we're doing. How should people start thinking about some of these pieces in terms of the different fluids that exist in the atmosphere, how these fluids actually interact with one another? For instance, you mentioned that methane is lighter than air, quote unquote. But truly it's lighter than the weighted average basket of compounds in the air because there's CO2 in the air. It's lighter than that, but it may not be lighter than some of the other things that are in the atmosphere at any given point in time. So I think it would be helpful to start syncing up some of these points for folks.
The for me, at least, going back to atmospheric dynamics, the easiest way to think about wind is actually to just keep thinking about mass. Don't think about pressure, because pressure is an interesting quantity, and there's a reason why that quantity exists, and that it has a historical significance because, 300 years ago we used barometers to measure this thing, and we could, but in the end it all comes down to mass and continuity and the conservation of mass, right? This is where wind comes from. If for some reason, say these two balloons here together represent a continuum of air, which is how we think about gases and fluids. We think of them as being a continuous blob. So this has to do with some of the mathematics involved. We know that that's not true. We know that there are molecules involved and space involved between those molecules, but there are so many of them in bulk that we think of everything as a continuous substance, right? So let's imagine that for some reason, and in this case, we'll say that the reason is the heating from the sun. Because of the heating from the sun on this balloon over here, on this chunk of air, for some reason, the sun heated it, and now it moved itself spontaneously up here. Well, what happened to the space that it occupied before? Did it turn into a vacuum? No, right? That would require a significant amount of energy to do that. That would be really, really difficult to do. What happens is that other masses of air have to rush in to fill that void. And if that keeps displacing up, then then other masses of air have to follow. And what happens is in the atmosphere, as masses of air are moved spontaneously by energy. So now we have to talk about mass and energy. And this is all we ever talk about, mass and energy. And they're interchangeable and so on and so forth. But it is the addition of energy onto mass that causes it to displace spontaneously, that causes other masses to have to move into that space in order to find equilibrium. And in doing so, look what happened. I moved one, the other moved horizontally. This is wind. Wind happens because of continuity. And it has to be that way. There is no other possible way that, the atmosphere can manifest itself. And this is why when we talk about atmospheric flow and wind, we talk about circulations of wind. And this is where the circulations come from. And you see that manifested in simulation in our tool. You see that when the animation is playing, you'll see the animation being broken up into what we call eddies, vortices, and elements like this. These are small circulations, and these circulations obey the conservation of mass because of this principle that air has to displace in occupied space.
Conservation of mass.
Yeah.
Hit on that a little bit more. Explain what that is.
It is the simple fact that every piece of regular matter, everyday regular matter under most of the general conditions in the universe, certainly the ones that we experience on this planet, we're not anywhere weird or interesting. We're in a place where matter is just matter and doesn't vanish or do anything fancy. So if matter exists, then it must continue to exist. And if that matter is in motion, then that matter continues to be in motion and exist in motion, and other matter has to occupy the space that it had before. And so these two masses have to conserve themselves, and they have to find a way to arrange themselves in such a way that the total amount of them is still the same, even though some energy was inserted into that system. And that's where the sun comes in. The sun is always supplying energy onto our planet and causing the fluids on our planet, the air, the water, and everything to move, continuously move in accordance to conservation of mass, right? It can't destroy the mass. It just causes it to move about each other in order to maintain that, try to find that equilibrium. If the sun were to turn off, for instance, then at some point, all motions would cease to exist, and we would just be living in a cold slab of all of the same mass that we had before, but everything would be probably frozen and would be dead.
Yeah.
But all that motion would cease. All that wind, all that current of water and air would cease to move.
So let's sync up a little bit of why this matters for methane, for dispersion, right? For the models that we build. So to go back over, air, just like water, just like this table, has mass.
Yeah.
Right? That mass is a fluid. It's moving about, at least when we're talking about air, freely in the atmosphere in many cases, but not always. We'll talk about obstructions and things like that, obviously, in the future. These balloons that you have represent whether it's air molecules or pockets of air and how they interact with one another.
Yep.
And so we're thinking about that. And then we're talking about the conservation of mass, meaning you're not destroying this. So even if you burn methane, I think a lot of people think that you may be not conserving the mass. All you're doing is chemically just altering the bonds, right? So the mass, you've actually destroyed nothing. You've just rearranged things. We can get into a future discussion of actually what happens with fusion. That's a whole different can of worms. So when we're talking about this, how does this have any implications on methane and how, if it's being released at a well site or at a landfill or at a dairy farm, why is it important to be thinking about this interaction?
Very simply, let's go back to the methane here. Okay, so let's say this chunk of methane that I'm interested in, it's in a pipe initially, or at least prior to being in the atmosphere, it's in a pipe or in some equipment, and it's contained. And we could go to that piece of equipment, and because it has fixed dimensions, because it's contained in such a vessel, we could measure its density, and through a fairly simple calculation, determine exactly what the total mass of that is. Now, what happens if we don't do that and then there's a leak and some of that mass then gets released into the atmosphere? Then that mass is now subject to everything that's happening in that local atmosphere. All of the wind, all of the complicated wind, all of the simple wind. Sometimes there's no wind. I mean, you've shown cases in the simulator tool where you have no wind. Well, what happens when you have no wind? Well, the stuff still disperses into a still atmosphere. You can have a still atmosphere. You can have a moving atmosphere. You can have an atmosphere that's aggressively moving in various different ways that we pretty much understand fairly well in terms of the atmospheric dynamics. Now, that mass of methane is now subject to all of those motions and begins to take up those cavities and spaces and move along those complicated wind fields. So what happens is if you have a sensor or a detector of some type that's out there measuring concentrations of methane at some location close to where you suspect that a leak might be, what you're picking up on is a methane that's already been displaced and moved around in this complicated atmosphere. You're catching a little glimpse of all of that dispersed. So imagine a way to imagine this is imagine you have a cup of water in front of you and you just tip it over and watch the water flow in front of you and disperse itself around. It's the same amount of water, right? By conservation of mass, it's the same amount of water, but it becomes a lot more difficult to know how much of it is when it's all strewn around on the table. Back when it was on the glass, you could measure the glass and figure out exactly how much water you had. But now afterwards, once it has been subject to its fall and dispersion, now it becomes much more difficult. Now imagine that you can only sample a drop of that at some place on the table. And based on that, try to figure out how much water actually fell out of that cup. That's the kind of problem that we're talking about. And it's not easy, but it is possible. And what allows it to be possible is precisely conservation of mass. Because we have that constraint, and because we rely on that constraint, because we know that that must be true on this planet, we can actually make the computations and create models that allow us to reverse engineer that process and almost look back in time and get back to a situation where we can say, okay, this is the amount of mass that had to have fallen out of the glass in order to flow around onto the table and become that particular footprint of dispersed fluid.
And just to frame up, I guess, how infinitely complicated it could get is if we knocked over that glass of water and spilled on the table and we didn't pick it up and we sat here for a day, all of that water would eventually evaporate into the air. So the person who would come here after you wouldn't even be able to see the water on the table. But because of the conservation of mass, it's actually in the air around us. Yeah. So put differently, you would still be able to calculate, assuming everything else was steady, the change in absolute humidity within the room itself, and therefore know that there must have been water spilt on the table, and you could exactly back out how much water was spilled on the table just by looking at that.
As long as you know that there was a change in these conditions and somehow be able to measure them.
So you mentioned that methane was lighter than air, quote unquote. Why does that matter?
It matters because it affects its motion. So it's like saying that, so we did say that in general, and most of the time you can say that air moves methane, right? Because air is much more, in the situations that we're talking about, the amount of methane that's being released is far smaller than the amount of air that's in the local atmosphere, right? So the currents of air are moving the methane. It's kind of like saying, is the dog wagging the tail or is the tail wagging the dog? So clearly it's the first one, right? Because the tail is smaller and this is bigger and this is much more massive in terms of its energy, and it's moving the methane around. But there are situations in which methane can spontaneously become buoyant, or meaning that it can float relative to the local air, just like we can float relative to water. People float, right? You get in the pool and you can float. That means that you're literally lighter than water. So methane will float relative to air, and in that respect, it'll spontaneously move vertically relative to the air. And by vertically, I mean against gravity, right? Gravity is the thing that keeps us all kind of locked down to the surface. But to be buoyant means that you can move against gravity spontaneously. And sometimes methane can do that, and it has to do with its density relative to the local air. In this case, this balloon is smaller, this balloon is bigger, this has less mass than this one, so this one is buoyant relative to this one, and so it'll displace itself vertically. That matters in a variety of different ways, but it matters in the fact that it is motion that isn't dependent on the wind. It's motion that's spontaneous to the gas itself. And that's an important thing to include in the way that we model and the way that we measure, because it has implications as to whether or not you can actually solve the problem of saying, okay, how much of that methane came out? If it's behaving in this way and you don't account for it, you get a completely different answer.
So one of the questions you'll hear people ask a lot is, so what? Methane is lighter than air. So to take it to the next, conclusion, if methane is lighter than air, why then is there methane in the atmosphere, roughly 1.8, 1.9 parts per million at the ground level? Put differently, if methane was lighter than air, why wouldn't it have all floated to the top of the atmosphere? The same way, if we mix oil and water, the two will separate and one will float to the top.
Because, very simply put, methane is lighter than air until it isn't. So, and this is one of the fundamental parts about atmospheric dynamics on this planet, that our atmosphere is stratified, and that means that we're under gravity. So that means that the density of our air decreases with height. So at some point, if you're thinking about parcels, if you're thinking about these balloons or a parcel of methane will be buoyant relative to the air until it reaches a level when it isn't, when the density of the ambient air is the same as the density of that local methane. And at that point, buoyancy ceases to be a factor in its motion. And so then its motion becomes more dominated by the local wind field. And because it's dominated by the wind field, then the methane begins to mix out. So eventually the methane will mix out uniformly into the atmosphere. Under stratification, that keeps a uniform concentration of methane that is building up as more methane is being released into the atmosphere. So these buoyancy effects are very local. And the reason we worry about them is because we put our sensors very near the sources of these emissions. And so we worry about the things that are the physical factors that are changing the concentration of methane very local to the places where they have been released. Once a significant amount of time has passed and enough motion has happened, then you essentially just get uniform amounts of methane into the ambient atmosphere that now become additive. But it's in that local area, it's in that near emission atmosphere that we worry about turbulence, eddies, and buoyancy of methane in terms of how to know where those concentrations are going to be laid out to be measured and then quantified.
So then as you think about this, like over what time period then do these effects all start to average out?
That's very much dependent on on what the atmosphere is doing. And we're at the mercy of the atmosphere in this case. So if it's, let's say it's, then we have to start to list scenarios here, right? So you have a very windy day, the wind is tearing through a site and it picks up the methane, and there's a lot of, what we might call mechanical turbulence, meaning the wind is blowing so fast that it just breaks up into all these eddies. And we experience this like when a thunderstorm comes through and puts out a gust of wind, and you feel a rush of wind that appears to come from all directions as it hits you, out there when you get a little gust of wind from a thunderstorm, right? That's turbulence. That's eddies and rolling motions of air in all kinds of directions. And that acts to mix anything that's concentrated. If there's anything that's concentrated in the air, like methane, it will get mixed out in those motions, meaning it will tend towards a uniform state. And so in a very windy day, the methane will mix out very quickly. So in a matter of minutes, you have a situation where you have concentrated amounts of methane near the sources, and then all of a sudden now you have just ambient. You can't discern anymore where those concentrations are.
It depends, right? Exactly. So I just like to say, if you poured creamer into coffee and you just let it sit there, it takes a while for it to obviously make its way around the coffee. If you immediately take that coffee and pour it into another cup, it's pretty well mixed pretty quickly, right? Because obviously you're having much more mixture as you poured it from one cup to another. I guess you mentioned the word stratified, right? And then you were also just talking about whether or not the air is mixing or how quickly it's mixing, I should say. And so one of the things that I did is a video on the dispersion of methane when you have very low wind speeds. And so in that video, I said, we'll talk about this later, but one of the things that's happening is a low planetary boundary layer that's effectively causing ridiculously low wind speeds at certain time periods. We don't necessarily need to go into the why. We'll touch on that in a second, but talk about this idea of stratified air. I don't think people fully appreciate that it can look more like a layered cake in some cases, right? Than it is just a nice open mixture of what's in this case a mass of air. Can you talk a little bit about like planetary boundary layer, stratification of air, thinking about this in terms of layers? Oftentimes you look at different portions of the atmosphere and you can have wind heading in the opposite directions, right? You have the jet stream going one way, you have the wind obviously on the surface going another. How should we think about that stratification? What those layers look like, where those layers are, how thick those layers are, how those layers change over time, what the implications are for the layer underneath the layer above it, right? How do these things interact with one another?
Okay, so let's start with stratification. That the word stratification comes from gravity. It's gravity that's doing this. So gravity is causing the air. So the gravity is what holds the atmosphere onto our planet, right? If we did not have gravity, if we did not have something to hold on to our air would have already been blown away by,
So fun fact, why does the moon not have an atmosphere or Mercury not have an atmosphere? It's because it lost, obviously, its magnetosphere, even though it still has the gravity. We'll talk about that at a fun, like a segue. So there's other forces in addition to gravity that you need to retain an atmosphere.
But in general, it's gravity that's holding our air onto the ground. And it's holding us onto the ground. Anything that's on the surface is being held onto the surface of this planet by gravity. Now, air happens to be a fluid. It happens to be a gas. And so that gas will squash down by gravity. While something like this table that is solid is affected by gravity almost uniformly from top to bottom, right? Because it's solid, right? There's no way I can squish this. So there's no space or no way that gravity, at least the gravity that we have, can squish it. But gravity actually squishes the air towards the bottom surface. And that's what makes stratification happen. That's what puts relatively more air at the bottom of our atmosphere than at the top of our atmosphere by a significant amount. And for anyone that's ever climbed a mountain, you know that as you're ascending a mountain, you're having a harder and harder time breathing. That is because there's literally less oxygen. So there's less air for you to breathe.
We'll get that. That makes sense, right? You're squishing everything down. But then why are there different layers of the cake, right? Why wouldn't it just be all squished down and have equal composition and equal flow? What is with this whole thing in terms of the layers of the air themselves and how you could have wind headed in different opposite directions sometimes from one layer to another? Like, what is causing that to happen?
So there's two things that cause the squishing to not be uniform, to not just simply, squish the atmosphere to be a certain height that would be less with gravity. It's the fact that gravity is a gas, the fact that it compresses and that it'll compress down because there's more gas above it. And so it doesn't compress uniformly. It compresses in a way that is not uniform. And that has to do with the fact that it's a gas. It's really just a function of the fact that it's a fluid. All fluids stratify in a non-uniform way. They don't squish regularly under a body force. That's the other thing. Gravity is a body force, and it's a body force that is changing with height. So the further you are away from the surface of the earth, the relatively weaker gravity is. Gravity is a little bit stronger down at the surface. And so it pulls more of that air down, compresses it more relative to the air that's at the top of the atmosphere. And so all of those things put together lead you to an atmosphere that is stratified non-uniformly. It looks like if you were to look at the density of air with height, with elevation, you'd see something that looks like a slide. So it becomes much denser towards the surface of the earth than at the top of the atmosphere.
So when we're talking about like this low wind speed conditions and methane pooling at a facility, or really whatever is being released in many cases, that low planetary boundary layer, like, I guess, take a step back. What is a planetary boundary layer?
So this is boundary layers. Let's talk about just boundary layers in general, right? And so as a fluid moves across a solid surface, so the surface of our planet is a solid surface. So as this fluid moves along a solid surface, the condition at the boundary is that there's no wind, right? There's no wind exactly at the ground. At the ground, there's zero wind. There has to be, right? Otherwise, our Earth would be moved or something would be happening, right? You would feel the friction of that. But what happens is that because there's zero wind at the ground and there's wind in motion about very near the ground, you begin to mix out very near the surface. And that layer where things are very mixed out and all of the near surface dynamics are going on, all of these eddies and turbulences and gusts and the wind flowing across a tree and breaking up in front of a tree by your house, and all of these things that are happening that are mixing out quantities. So the way we understand a planetary boundary layer is this is the height up to where most of the quantities in the atmosphere are mixed out uniformly.
Okay, so this is important because you're using terms near, and every discipline has its own, like, it's like if you talk to someone who works in a discipline where they're talking about ancient Earth, like they talk about near term as like 100,000 years, right? Yeah. So when you say near the Earth, when I think near the Earth, many other people think near the Earth, they're thinking like 6 feet, 3 feet, 2 feet. Obviously, you come from NOAA. What when you're saying near the Earth for this boundary there, what does that mean?
We're talking about a kilometer, usually between 1 and 2 kilometers, depending on the situation. And that situation has to do with energy, right? The more energy. So if you can think of the surface of the Earth as a hot plate. So when the sun is shining down on it, like this light, it's heating it up. It's heating up this hot plate and literally putting energy into that very near it. So the air that's in contact with the ground is being energized by the temperature of the ground. And that causes that air to spontaneously begin to move upward, right? Because that hotter air expands, suddenly becomes lighter than some of the air around it. So that begins to produce motions that are up. So the balloons begin to rise. If the balloons rise, then that means that air has to be moving underneath in order to compensate. It has to by continuity, by conservation of mass. And suddenly you get motions of air that are like this, rising motions of air that sometimes can turn sideways, and you get things like dust devils that occur in the planetary boundary layer. And sometimes the height of a dust devil, or the height of dust devils are actually great because you can tell the height of the boundary layer by looking at a dust devil, by seeing how tall it is. You can actually measure exactly where the height of the planetary boundary layer is. You can get a good feeling for that.
So when we're talking about, again, low wind speed conditions, low wind speeds, right, resulting in the pooling of methane due to that low planetary boundary layer, what is causing the planetary boundary layer to move to a lower altitude?
It's at night. Usually this happens at night, nighttime conditions, very calm air. So imagine the atmosphere is very, very still. It's nighttime. The ground begins to cool. It's clear also. There's no clouds. So the ground is open to space. What actually happens is you get what's called radiative cooling. So you get literally the flow of energy from the ground into outer space that's causing the ground to cool faster than the air around it. So instead of acting like a hot plate, now it acts like a cold plate, causing air to get denser near to the ground. And basically shutting down all of those motions that I was talking about. So all of these things that were going on when the sun was out, that were moving around, dust devils and eddies and things like that, all of those shut down as the ground begins to cool faster than the air around it. It literally begins to lower that level at which we can consider that all of those quantities are mixed out. So then the planetary boundary layer gets low, very, very low at night.
So I guess this is a good point, Jorge. Does the low wind speed condition cause the low planetary boundary layer, or does the low planetary boundary layer cause the low wind speed?
There's no cause and effect relationship there. I mean, the low wind speed is a factor, but say for instance you had low wind speeds, but you had a very cloudy sky at night, then you wouldn't have the radiative cooling as quickly.
Because the clouds are acting as a blanket.
As a blanket, preventing the ground from radiating that heat away, which you would still get the cooling from the nighttime conditions, but you wouldn't get it as much. Humidity and moisture has a big effect in the atmosphere. In fact, one can argue from atmospheric dynamics that humidity and moisture has the biggest effect next to the sun. So what drives our atmosphere is the sun and water, and the way water behaves in our atmosphere. Those are the two things that are actually causing things to happen. Now, I think that's to get into moisture and the way moisture affects atmospheric dynamics, like, I'm gonna have to think about that, and we can get into that.
Parts 1 through 10, right?
Because that's an entire course. But but it's air and water. So it's air. The sun injecting energy into the ground. That then gets transferred onto the water, which evaporates into the atmosphere and drives energy into the atmosphere. But as far as the planetary boundary layer is concerned, a low wind speed condition can arise from a variety of situations that are not just local, but also much bigger than local. So we're talking about, low wind speed conditions that are due to giant high pressure systems that are, the size of the country. And underneath those, the wind speed is low. And so it's hard. A lot of times in atmospheric dynamics, it's hard to go after causes and effects. It's more correct to think about dynamics between phenomena. So low wind speeds at nighttime, coupled with a clear sky, induces a situation where the dynamics dictate that the boundary layer must be lower in order to make sense of all of those pieces together, rather than saying low wind speeds cause. It's more about consistency. Like those three things are consistent together.
Jorge, one thing that I think is important to know is like, why are you well-versed in talking about these topics? I guess, what brought you to this point to understand how all these forces interact with one another?
I'm an atmospheric scientist, and I fell in love with atmospheric science as a young boy when we first moved to the United States. We moved to Miami, Florida in 1991, and we went through Hurricane Andrew in 1992. And at that point, I became fascinated with the weather and with the atmosphere. I had no sense when I was young that I could be an atmospheric scientist, so I became an aerospace engineer, and I worked as an aerospace engineer for a long time. I became interested in computational fluid dynamics, and I did all sorts of computational work, solving partial differential equations and all these things. And eventually I decided to go back and get my PhD and do it in atmospheric science. And at first with the idea of being an academic and working in research, until I found Project Canary, and a way to be an atmospheric scientist in a setting that was different, fresh, and very innovative.
So, Jorge, heard a lot of cool stuff to hear. It's fascinating to hear about these early foundational blocks that are so important to understand something as simple as wind. So appreciate you taking the time to dive into this stuff today.